Hello, curious minds. Imagine a planet so close to a dead star that it's constantly bombarded with deadly radiation. These are pulsar planets, worlds that shouldn't exist, yet somehow do. Today, we're diving into one of the strangest cosmic mysteries in the universe. Pulsars are highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation. When these beams are pointed toward Earth, we perceive them as pulses of light, much like a lighthouse. Pulsar planets are those rare planets that orbit these exotic stellar remnants. Their environments are extreme, often exposed to high levels of radiation, making them drastically different from the planets we know. The existence of pulsar planets comes as a surprise to many astronomers. Normally, when a massive star ends its life in a supernova explosion, the resulting chaos obliterates anything nearby. So how could planets survive this cataclysmic event? This discovery challenges our previous notions of planetary formation and survival in the universe. Studying pulsar planets is crucial for several reasons. First, they provide a unique opportunity to examine planetary formation in extreme environments. Moreover, pulsar planets help us refine our models of how planets develop and evolve in various cosmic conditions. So, as we explore the mysteries of pulsar planets, we open a door to new possibilities about where and how planets can exist. The first pulsar planet, PSR B1257+12b, was discovered in 1992 by astronomers Alexander Wolszczan and Dale Frail. Using the Arecibo Observatory in Puerto Rico, they detected irregularities in the timing of the pulsar's signals. These variations indicated the presence of orbiting planets, a groundbreaking find, as it was the first time planets were discovered around a pulsar. It challenged the prevailing notion that planets only existed around main sequence stars like our Sun. PSR B1257+12b, along with two other planets in the system, orbit the pulsar PSR B1257+12. PSR B1257+12 is a millisecond pulsar located about 2,300 light-years away in the constellation Virgo. The system contains three confirmed planets named PSR B1257+12b, C, and D, with two of them having whimsical nicknames, Poltergeist and Phobator. Poltergeist, the innermost planet about 0.02 times the mass of Earth, is believed to be a rocky body with a surface constantly bombarded by radiation from the pulsar. Phobator, a slightly more massive planet, approximately 0.26 times the mass of Earth, also likely features a rocky composition. The third planet, PSR B1257+12d, is the most massive of the trio, with a mass roughly 4.3 times that of Earth. Its characteristics remain less understood. This discovery proved that the universe is full of surprises. To understand pulsar planet formation, we must first consider the life cycle of massive stars. These stars shine brightly, but their end is explosive, often resulting in a supernova. This cataclysmic event can lead to the formation of either a black hole or a pulsar. Today, we'll focus on pulsars, rapidly spinning neutron stars that emit intense radiation. But how does this violent transformation allow for the creation of planets? Traditionally, planet formation requires a protoplanetary disk, regions of gas and dust where planetesimals can form. However, the situation around pulsars is quite different. Due to their high luminosity, pulsars can ionize their surrounding disks, preventing the formation of a dead zone, a calm area essential for the accretion of material into planets. Without a stable environment, planetesimals struggle to form. There are three main generations of pulsar planets, each with unique formation mechanisms. First-generation planets are planets that orbited a massive star before it went supernova. However, massive stars tend to lack planets due to the destructive radiation that inhibits the formation of protoplanetary disks. If any planets were in close proximity, they would likely be destroyed during the star's red giant phase or supernova. As a result, no known pulsar systems formed from this generation. Second-generation planets would theoretically form from material that falls back onto the pulsar after a supernova. While this material could reach sufficient mass to create a disk, it often dissipates too quickly, preventing stable planet formation. To date, there are no known examples of planets around young pulsars. Third-generation planets arise from the destruction of a companion star. As the pulsar emits energetic radiation, it can heat the companion star until it overflows its Roche lobe, eventually leading to its disintegration. This process creates a low-mass disk around the pulsar. In some cases, gravitational waves can shrink the orbit of a companion star until it breaks apart. Or, the pulsar may penetrate the envelope of a larger star, causing a similar outcome. Additionally, pulsars may capture rogue planets, those wandering freely in space without a parent star. Due to their strong gravitational fields, pulsars can draw in these free-floating planets, adding to their planetary systems. One of the biggest questions surrounding pulsar planets is how they could even form, survive, or thrive in such an extreme environment. A pulsar's radiation and magnetic fields are incredibly intense, capable of blasting away most nearby material. So how did planets like PSR B1257+12, C, and D come to exist so close to their pulsar? And how do they persist despite the ongoing radiation? The next big question is how these planets originated in the first place. Scientists have proposed several theories, such as the third-generation idea, or the possibility that rogue planets drifting through space were captured. Alternatively, could fallback material from the original supernova somehow provide enough matter for planet formation? The question remains, which one is right? Another mystery of these planets is their surface. We've barely scratched the surface of what these planets are like up close. Pulsar planets exist in a hazardous environment bombarded by constant radiation and energetic particles. Are their surfaces barren, scarred, and devoid of atmosphere? Or could there be unique adaptations, strange magnetic fields, or mineral compositions that allow them to endure? The next question may seem far-fetched. In such extreme conditions, could life ever emerge or survive? While it seems nearly impossible, some scientists wonder if microscopic extremophiles, organisms adapted to extreme radiation and harsh environments, might be able to exist on or within these planets. The existence of life here would require us to completely rethink the boundaries of habitability. One final mystery is whether pulsar planets are more common than we realize. Detecting pulsar planets relies on tiny variations in pulsar timing. But what if there are planets whose influence is too faint for us to pick up with current technology? Are there entire populations of small or distant planets we're missing simply because their signals are too subtle? The mysteries of pulsar planets stretch the boundaries of what we know about planets, stars, and even life itself. As our technology advances and our exploration deepens, we may uncover more answers, or encounter even stranger questions. To sum it up, pulsar planets challenge nearly everything we thought we knew about planets and their formation. What do you think? Could there be even stranger worlds waiting to be discovered around other dead stars? Let me know your thoughts in the comments below. And if you enjoyed this journey into the cosmos, don't forget to hit that subscribe button for more mind-bending space stories. Thank you for watching. Until next time, keep looking up.